So let's continue where we left from. Just let me quickly take a recap. And we said that we are going to put the fins or extend the surface by increasing the area, because that's the cheapest way instead of increasing the heat transfer coefficient or decreasing the T infinity, which involved the pumping power, that is increasing the active power cost. So the surface area increase, how best we can increase the surface area was the question. And there are various applications of the cooling heads and of the motorcycles or cooling electric power transformers or various heat exchangers. We are going to use these fins, and these fins can be of different shapes: rectangular, triangular, circular, or varying cross section. So we did the general conduction analysis of the extended surface, and we did the energy balance, and we came up with this equation. This is the general conduction equation for the fins. But if we consider the constant cross sectional area, my equation reduces to this, where this is a second order linear homogeneous differential equation. So this is second order, so the solution is of this type, and there are two constants. To get these two constants, we need two boundary conditions. So we said that the base temperature we have to prescribe, or we should limit the base temperature, because in any design you don't want the base temperature to exceed a particular temperature. So that's why the base temperature is usually taken as a constant base temperature. Not that we cannot solve for other conditions, we can solve, but this is a design condition. And the other, at x equal to L, that is at the fin tip, you can either have convection or adiabatic or a prescribed and the infinite. We solved in the last class these three cases. So today we shall take up convective heat transfer from the fin tip. So if the convective heat transfer is there from the fin tip, convective heat transfer from fin tip. So you have theta of x equal to C1 e to the power of mx plus C2 e to the power of minus mx, and theta at x equal to 0 is theta b, and let me remind you, theta of x is nothing but t of x minus t infinity, and at x equal to L, at x equal to L, at x equal to L, so it is convective boundary condition. That means you have q dot equal to, at x equal to L, h AC into T of L minus T infinity is equal to minus KAC dt by dx at x equal to L. This is nothing but h into theta L, AC gets cancelled, so minus k, this is nothing but d theta by dx at x equal to L. This is theta equal to x equal to L. So let us just get the algebra going through our PPT. So you have this, so you have the two constants. So if you just substitute theta 0 equal to theta b, that is theta b is equal to C1 plus C2, and h theta L. So h into theta L is nothing but C1 e to the power of ml plus C2 e to the power of minus ml is equal to Km into C2 e to the power of minus ml minus C1 e to the power of ml. If you just do the algebra solving for C1, C2, you get this temperature distribution. So what are the steps involved in getting that is that this is one equation. So if you substitute C2 equal to theta b minus C1 and just do various steps, I would strongly recommend you don't skip any of these steps. They are there here in this video. Please write down everything yourself. I have put every little step here. If you do that, you get C1 as this, and then once you get C1, you have the C1 as this, theta b equal to C1 plus C2. Substitute for C1 and do the algebra, you get C2 as this term. So I strongly recommend, please do not skip the steps, do it yourself. In most of the books this is not given, that is the reason why I have added this for your benefit. So please do this and get this C2. Once you substitute C1 and C2, so you get the temperature distribution in terms of M, L and X. So further algebra of this will lead to cos hyperbolic blah blah blah. So this is your temperature distribution, what you will get for the prescribed, for the convective boundary condition. So now for the heat transfer rate, so what is the heat transfer rate? Ka dt by dx at x equal to L. So if you get the heat transfer, that is Q equal to Kac dt by dx at x equal to L, and that is you differentiate, this is your temperature distribution. If you differentiate this, so you get minus m sin hyperbolic m L minus x and cos hyperbolic m L minus x, and substitute x equal to 0. So you get the heat and do the algebra again, do the algebra, you get Q equal to theta b into square root of Hp Kac and whole of this. So please do not skip these steps. My humble request is not to skip any of these steps, write down everything and get Q equal to this. So once you get this, so everything is summarized. For 4 boundary conditions, 4 tip boundary conditions, we have gotten the temperature distribution, we have gotten the fin heat transfer rate. Now the next issue is, now what should be the proper length of the fin? So it would be, if you just really see the temperature distribution, if you just see, it is exponentially decreasing. So having a long fin is not of much use. If you just see that this is the temperature distribution and this is the x. So you can see that for shorter duration, for shorter length, there is high heat transfer taking place, and here low heat transfer, and here after certain length there is no heat transfer taking place at all. So there is a particular length beyond which there is not much benefit of putting the fin. So what is that length, proper length of the fin, is the next question. So to get that, let us compare the Q fin with the adiabatic fin tip with Q fin with the infinitely long tip. That is Q fin. You can write the heading as proper length of fin. That is Q adiabatic fin tip divided by Q infinite fin, infinitely long fin, that is equal to theta b into square root of HPKAC tan hyperbolic ML divided by theta b into square root of HPKAC, that is equal to tan hyperbolic ML. So the question is, when does the Q adiabatic fin approach as if it is infinitely long fin? When tan hyperbolic ML is almost 1. So let us watch how does tan hyperbolic ML vary with ML. So if you really see, this is the ML and this is the tan hyperbolic ML. So around 2.5, the tan hyperbolic ML is 0.987. So you may not really want to use an ML of 5. If you take ML of 2.5, your length of the fin is almost half. The cost will come down significantly. Remember, you are making the fins with copper or aluminum. Copper is like gold today, it's very expensive. Aluminum is also no cheaper. So you need to cut costs but not forego or compromise the heat transfer rate. That can be achieved. So somewhere around ML of 2.65 or 2.5 would suffice, and fin with adiabatic fin tip would behave as if it is a infinitely long fin. So that is, so now let us take up a problem where a very long rod, to understand all of this, to put things in perspective, let us take a problem where a very long rod of 5 mm in diameter has one end maintained at 100 degrees Celsius and the surface of the rod is exposed to ambient air at 25 degrees Celsius with a convection heat transfer coefficient of 100 watt per meter squared Kelvin. Determine the temperature distributions along the rods constructed from pure copper fin and aluminum alloy and type AISI 316 stainless steel. So, what are the corresponding heat losses from the rods? Estimate how long the rods must be for the assumption of infinite length to yield an accurate estimate of the heat loss. While we solve this problem, immediately after this problem what we will do is we will study what is called as fin efficiency, and after fin efficiency we will study what is called as fin effectiveness. So, let us solve this problem little slowly and try to understand what is involved in solving this fins and how do we choose the fins. So, let us put the, so you have a fin, so given, what is given is, it is a fin, diameter is given to be 5 mm, diameter is given to be 5 mm and the surface of the base temperature, the convection, the surface of the rod is exposed to H equal to 100 watt per meter squared Kelvin and T infinity is 25 degree Celsius, okay, 25 degrees Celsius. And what else is given? That, and we have been given three materials: copper, aluminum and stainless steel. Three materials choice we have been given, and we need to take the properties of these materials. At what temperature will we take? And the another thing which we have been given is that the base temperature, see the long rod in diameter has one end at 100 degree Celsius. So, that is TB is given to be 100 degree Celsius. So, at what temperature I should be taking, because I know these two temperatures. So, I take TB plus T infinity by 2, that is 100 plus 25 by 2. So, that is 62.5 degrees Celsius or 335 Kelvin. So, at this temperature, so the copper is having a thermal conductivity of 398 watt per meter Kelvin, and aluminum is the next, it is almost half of it, 180 watt per meter Kelvin, and stainless steel is very low, 10 times lower, 14 watt per meter Kelvin. Okay. So, now with this, now let us calculate with, if this is known, let us take infinitely long fin, infinitely long fin. If I take infinitely long fin, so what is that? I am going to get the temperature distributions are T, I know that I have gotten that as theta equal to theta b into e to the power of minus mx, that is T of x minus T infinity equal to Tb minus T infinity into e to the power of minus mx. Now, m squared is equal to, or m is equal to square root of Hp by Kac, and also I know q fin is equal to square root of Hp Kac into theta b into theta b, where theta b is again Tb minus T infinity. So, now let us calculate m. So, m equal to square root of h into perimeter, this is a circular pin. So, your perimeter p equal to pi d and AC is pi d squared by 4. If you substitute h into pi d divided by k into pi d squared by 4. So you get m equal to square root of 4h by kd, 4h by kd. If you substitute, now for example, for copper, m of copper, if you substitute 4 into h is 100 divided by thermal conductivity of copper is 398 into diameter is 5 into 10 to the power of minus 3. So m of copper happens to be 14.2 meter to the power of minus 1, and aluminum, m of aluminum is 21.2 meter to the power of minus 1, because k is in the denominator, so m increases. M of stainless steel is 75.6 meter to the power of minus 1. So with this, now let us see how does, now can I plot this temperature distribution with this m? Yes. So I can compute T of x minus of 25, or T of x equal to 25 plus Tb is 100 minus 25 into e to the power of minus m, for example copper if I take, minus 14.2 into x. So at any x I can get the temperature distribution. So if I plot this temperature distribution, so it will look something like this. Okay. So let us show this plot in the PPT. So if you see here, you can see that this pink color thing is for copper, and for aluminum it is red, and blue color is stainless steel. So you can see that the copper, stainless steel is actually reaching its temperature in a short length, and aluminum takes longer length before it reaches the base temperature, right, and that is before it reaches the T infinity. So here it is starting from 100 to 25, stainless steel reaches very quickly, maybe around 50 mm, but for aluminum it reaches maybe around beyond 200, but for copper it still takes longer lengths. Now the question is, should I go for copper, should I go for aluminum, should I go for stainless steel? We have gotten only half of the story, that is temperature. We need to get the heat transfer rate also. So how do I get the heat transfer rate? Though I will show you for one and write for the other. So Q fin is equal to Tb minus T infinity into square root of Hp KAC. So Tb is 100 minus 25, 100 minus 25 into square root of 100 into perimeter is pi d, pi into 5 into 10 to the power of minus 3. K of copper is 398 into pi by 4 into 5 into 10 to the power of minus 3 squared. So Qf of copper is equal to 8.3 watts. Similarly, if you do for Qf of aluminum, you get that as 5.6 watts, and Qf of stainless steel you get 1.6 watts. So now you see, if you go for copper, you can dissipate maximum heat transfer, that is 8.3 watts, but of course you have to take little longer lengths. So now what should be the length you should take? So you know that in my earlier slides I had shown you that, if you recall, what should be the ml so that it becomes infinite. I had told that, you see here, ml, Q fin adiabatic divided by Q infinitely long tan hyperbolic ml. It reaches almost 1 with an ml of, you can even take 2.5. Let me go ahead and take it as 2.65. So if I take 2.65 as my ml, that is, I am considering that the Q fin, that is tan hyperbolic ml, approaches almost unity for an ml of greater than or equal to 2.65. So, if I take ml of 2.65, so m into L equal to 2.65. I have gotten m of copper. I have gotten m of copper as 14.2 meter to the power of minus 1. So, 14.2 into L of copper equal to 2.65. So, L of copper is equal to L infinity, that is L infinity of copper equal to 0.19 meters, L infinity of aluminum equal to 0.13 meters, L infinity of SS is equal to 0.04 meters. This is very interesting. You see that if stainless steel is effective as a fin only up to 0.04 meters, that is why it is able to take away the heat only from the base of 1.6 watts. On the other hand, if you take aluminum which is of 0.13 meters, which is considered beyond 0.13 meters, it is of no use. It can dissipate a heat of 5.6 watts, which is definitely greater than 1.6 watts. Now, if you go to copper, you can utilize the copper up to 0.19 meters and it is taking away 8.3 watts. So, generally we do not use stainless steel fins, we generally use either aluminum or copper. Ideally we would like to use copper, but copper is very expensive. So, if you cannot afford copper, we will reconcile with aluminum. But you are now understood why we choose a particular material and what should be its corresponding length. If you were to take only the temperature distribution, you would have been at loss. This is SS, this is aluminum, this is copper. You would have been at loss whether to choose for SS or aluminum or copper. Because we know the Q fin and we know the length how much we should take, now we are confident of choosing what should be the length and how much heat it will dissipate for a given application. So, now there are two parameters which we need to understand, that is fin efficiency and fin effectiveness. Fin efficiency and fin effectiveness. So, in today's lecture I will be able to complete the fin efficiency, and in the next class I will define what is fin effectiveness and connect one with the other. If you know one, how to get the other. Okay. So, now next question is fin efficiency. Heading is fin efficiency. Okay. So, if you have a surface, like this, and this is your base area is equal to width into thickness, okay, and this is your base temperature Tb. Okay. Now, you put a fin. Now, you put a fin there, okay, you put a fin there, right. Now, this fin length is L and this is having width W and this is thickness T. Okay. Now, surface of the area of the fin, here we get confused, that is why I want to write, I have drawn it slowly. Why? Because we should not be getting confused. Area of the fin is, one is this bottom area, the top area, that is the top area, this area, that is W into L, that is top, and similarly you have the bottom, so you have 2WL plus into W into T, W into T. So, if the thickness is very small you can neglect this, but otherwise area of the fin is 2WL. If thickness is very small, you can approximate area of the fin as 2WL. Okay. So, fins enhance the heat transfer by increasing this area. Okay. So, Q dot convection now is occurring because of both fin and the unfin. So, now Q dot convection is equal to H into area of the fin into TB minus T infinity. Now, this is what is going to happen. So, now let us consider a fin of constant cross sectional area AC equal to AB. This time the heat will flow from conduction from the fin to the surrounding medium by convection with the same heat transfer coefficient H. So, in the limiting case of the thermal conductivity, infinite thermal conductivity, the temperature of the fin will be uniform. But if there is a K, the temperature exponentially, we saw that temperature drops exponentially for infinitely long fin. Now, if the fin is 100%, if the K is infinite, that is it is a pure conductor, infinite thermal conductivity, the temperature of the fin will be uniform, because there is no variation in the temperature because the K is infinite. However, in reality the temperature of the fin will drop like 80, 70, 65, 61, 58, 56, because it will drop because of finite conductivity. So, now this ideal case where K as infinite case, we will take it as ideal, and with that case we will compare our fin and then say that the Q fin and find the efficiency of the Q fin. So, that is efficiency of the fin is equal to Q fin divided by Q fin maximum. Q fin maximum. So, Q fin, for example, efficiency of, let us say I take efficiency of long fin, infinitely long fin is equal to Q fin divided by Q fin maximum. So, efficiency Q fin of long fin is TB minus T infinity into square root of HPKAC, but here it is H into area of the fin into TB minus T infinity. Okay. So, TB minus T infinity gets cancelled out, and I get here square root of HPKAC divided by H into area of the fin. Area of the fin is nothing but perimeter into length. So, I get 1 by L square root of KAC divided by HP. So, that is nothing but HP, this is nothing but 1 by L, 1 by ML, this is 1 by ML. Efficiency of the long fin is given by 1 by ML. Now, efficiency of the insulated fin tip, if I take insulated fin tip, so you can get TB minus T infinity into square root of HPKAC tan hyperbolic ML divided by H area of the fin. So, you get into TB minus T infinity. TB minus T infinity gets cancelled out. HPKAC divided by HPL into tan hyperbolic ML. So, you get tan hyperbolic ML by L into square root of KAC by HP, that is nothing but tan hyperbolic ML divided by ML. So, this is the insulated, this is the case with efficiency of the insulated case. Okay. So, as ML increases, the efficiency decreases. As the length increases, the efficiency decreases. It's quite obvious, because you don't want to have a longer length. Unnecessarily the efficiency increases because the temperature becomes more non-uniform. So that is what is going to happen here. So the fin lengths beyond a particular ml, you won't use. So efficiency beyond 90% you would not. If most efficiency of most of the fins used in practice is 90%. You would not like to go for fins beyond 90%. So I will talk about this fins little efficiency of the fins and connect this efficiency of the fin with effectiveness in the next class, and we will also solve a problem on this. Thank you.